Welcome back. So let me go recap a little bit what I was talking about. And so what I covered at the end of last lecture was looking at one term in the underlying Lagrangian, which is the one containing the pure vector fields, which looks like this, and analyzing it, pointing out that the fact that the fields, the light fields close into a light algebra, the light algebra implies that these type of structured constants vanish. And so, of the various coupling vertices that are allowed, that you may think exist, a few are absent, and in particular the one that has two light fields and one heavy field. I remind you, the A denotes a light field, the X a heavy field. That vertex is absent. So let me then come down to this statement here, that operators such as this one are necessarily loop generated, and argue how that happens. So for that, I'm going to use the board. Purple, not purple. Okay, so I have an operator that has three field strengths of the light fields. I know I've been calling them A, but since I'm going to talk about the standard model, I will use the notation I was using before and call the W's, and call them W's. These are the W's. Inside it are the W plus, W minus, and part of the Z and part of the photon. So the operator in question has W mu nu. I'm just going to write it symbolically, cube. The W in itself, the W mu nu, has two terms. One that has a derivative, and the other one that has two W's. The 2W term is precisely this one here. It's precisely this one here. And this is the derivative. This exact same form is followed by the field strength in the standard model. So when I do the cube part, I get terms that contain W to the n with n equal to 3, 4, 5, and 6. Yep. So the first thing I'm going to show is that by the way, if you have any process that at tree level can generate this operator, there ought to be some version of that process that generates the term with 3 guys and another at 4 guys, 5, all of them at tree level. Okay. And so I'm going to look at these 2 guys first. I'm sorry, not first, but only. Looking at number 3 first. So I'm looking for a graph that has 3 external legs and is a tree level graph. And for that, I'm just going to list the possible graphs that do that. So the number of loops of any graph is equal to the number of internal lines minus number of vertices plus 1. But I'm telling you, I need this at tree level. So this is equal to 0. Next, my vertices in the Lagrangian have either 3 or 4 fields, because the underlying theory is a gauge theory. So 3 and 4 fields. And there is yet another topological relationship that says this: the sum of the vertices with n legs is equal to twice the internal lines plus the external lines. The external lines are 3 for this case. I'm looking at generating at tree level an object that has 3 external W legs, so 3 external legs. And I is equal to V minus 1. So I have 2V minus 2 plus 3. What is V? Well, V is this number, the total number of vertices. So V, oh, I'm sorry, this is NBN. I'm sorry, NBN. V is the total number of vertices, so this is equal to 2, the sum of Vn plus 1. So what do we get? Solving this amazing relationship. We get 2 V4 plus V3 is equal to 1. V3 and V4 are numbers of vertices, so they're non-negative integers. So the only possibility for this, the only solution for this one is V3 equal to 1, V4 equal to 0. So the total number of vertices is 1. And by this expression, the number of internal lines is 0. So what I'm telling you is there's only one graph, one tree-level graph that can generate a 3-point vertex. And it's this graph with no internal lines whatsoever.
Can you please explain again?
Pardon me?
2v minus 2 plus.
Excuse me? This? Okay, so I expanded this, and there's a 3v3 plus 4v4. And then I put this thing on the left-hand side, and the 3v3 becomes 3 minus 2 is 1. This is the 1. And the 2v4 minus 4v4 minus 2, 4 minus 2 is 2. And you get equal to 1, this one.
No, I think she was asking about this replacing I by V minus.
Oh, this.
Yeah.
Oh, that's a topological relationship for the.
I plus E.
Yeah.
So I is equal to V minus.
Yes.
From number of loops.
Yeah, this is something that you prove in general.
Yeah, exactly. Follows from the previous.
What's that?
Yeah, this follows from this first line. That loop.
Oh, this follows from this first line. This first line follows by just analyzing how the delta functions work in a Feynman graph. Each vertex has its own delta function, and you eliminate all of them. There's one delta function left over for overall energy momentum conservation. Yeah, but it follows from this relationship. This is in any book in quantum field theory. In quantum field, I don't want to go through it because then I would have to start talking about Feynman graphs and expressing this thing in full detail. But this is a standard relation. Every book in quantum field theory has this expression. So it follows from once you substitute it. What I've done is I've substituted this V for I minus 1. I'm sorry, this I for V minus 1. All right. So this is the single graph that generates an object with 3 legs at tree level. At loop level, there's many of them. Okay? But our Lagrangian already has such a graph at tree level. It's the trivial contribution from the standard model. Among all the terms in here, there will be a series of terms where the little index A corresponds to the light generators. And those terms correspond then to the kinetic piece of the light gauge fields, which are precisely the terms in the standard model Lagrangian that we all know, and have nothing to do with the underlying physics in the sense that they don't involve lambda. So this is just the standard model. And this is not, the standard model and the vertex that can be is the one that comes from making a product, making a product of a derivative term and a quadratic term in an object such like this. The object that I'm looking at doesn't look like that. It's the cube of this guy has 3 derivatives, 3 gauge fields and 3 derivatives. The one that can be generated at tree level has 1 derivative and 3 gauge fields, missing 2 derivatives, if you wish. So the point of all this thing is that there is no way you can generate this object at tree level. It just doesn't happen. The structure of the theory does not allow it. And this is an example of what I call loop-generated operators. Independent of the nature of the underlying physics, this guy does not appear at tree level. So what does that imply phenomenologically? Yes?
If you relax the assumption that there is only one type of internal line,
Here.
so no, the first line, L
The-
equal to I minus B
Yeah,
plus 1.
no. There's no internal lines.
No, see, the first line, we have only I minus B plus 1, right? Yeah. We are assuming only one type of gauge boson, one type of internal lines are there.
So it's a question whether, if I'm assuming one kind of internal lines, the answer is no. Absolutely not. This is a completely general relationship for a graph that involves inside fermions, gauge bosons, or scalars. No assumption about this. This relationship is also true for all graphs. For all graphs. In fact, if you look in general, allow for a full effective theory where you have vertices with 3, 4, 5, 6, and so on, fields in them, 3 legs, this expression still holds. Where now it's 3, 4, 5, 6, 7, 8, blah, 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 kind of thing. Okay. But this is completely general. This comes out, again, of just counting when you put a graph, each vertex has to obey energy momentum conservation between each of the vertices. So these are the number of free integrations that you get after you impose energy momentum conservation at every single vertex. So the one triple gauge boson vertex that you can get at tree level is one that has 3 gauge bosons and 1 derivative. The one that comes from this operator has 3 gauge bosons and 3 derivatives. This guy, therefore, cannot be generated at tree level, must be loop generated, independent of the physics underlying the standard model. And this is one example of such iteration. So, for example, so what does that mean? It means that this guy, the operator that is this O, the coefficient for this operator, will have a 1/16 pi squared from the loops that has to generate it times the 1/lambda squared. So this represents an additional suppression for this operator. There are operators that do not suffer necessarily from this suppression, but this guy does. You will often see people talking about measuring triple gauge boson vertices. Those are these operators. They're talking about measuring this coefficient precisely. And when you get, for example, I think one example in the particle data book, it says that this is of the order of 0.1 TeV squared inverse. Okay, this is actual. They measured, I think it's the W photon coupling. And they put a limit on the difference between the W photon coupling produced by the standard model and use that deviations from that coupling, and they use that to put a constraint on DCO. Okay, this does not mean that the lambda is of order 3 TeV, which is what this would mean. But you're off by an order of magnitude. So instead of 3 TeV, you have a limitation of 300 GeV. And what you're saying is that there's no new physics at 300 GeV, which is true, but not new. We knew that for a long, long time, 10 years, long time. So it's powerful that the experimentalists can do this measurement. It's fantastic, but the physical implications from them are not particularly exciting because they chose an operator that is necessarily loop suppressed. And that is why this provides, I think, an example of why calculating or finding out which operators are loop generated and which ones may not has some use. Okay. So experimentalists go and they measure. The challenge is to extract CL or bound, put a bound on CL. That's their job. It might be very difficult, and that's why they do it. Our challenge is to take data and say what it has to say about nature. And for that, we need to understand how to translate a measurement to a physical parameter. And it's in that context that these statements that I'm telling you, that these calculations and these arguments are useful. Any questions about this? This is the main, yes, sir.
Here we are taking that I equal to 0 implies that this W cube has to be loop generated because if we have, let's say, W4.
Use the microphone. Okay.
Hello.
Yeah.
So here I equal to 0 implies that this W cube is loop generated.
No, yeah.
Yes, because there can't exist any internal line which implies any W, right?
Exactly.
So that's why we can't go, let's say, W4 that we can take. Only up to W to the power 3 we can take. That's why it is the case.
So, no, but I
Or-
can also say the same thing about 4 guys.
3 and 4.
I can do 4. I was going to do 4 right now. So bear with me for 4. Okay? Can do the same thing for 4.
Actually, I don't understand that how I equal to 0.
Means,
It implies.
means it's a graph without internal lines. It's a dot. No internal lines.
Yeah.
So it's this.
Yes.
This graph is this.
Yeah.
Okay, so what part of the Lagrangian has, this is just a term in the Lagrangian. So what term in the Lagrangian has 3 vector bosons? And I tell you, it's this times this. There's nothing else.
Yeah.
And this times this is derivative vector, vector, vector. The one I'm looking at is derivative, 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 vector, vector, vector. I'm missing 2 derivatives. So the only vertex that can, the only thing that Lagrangian can provide is this times this, the one at tree level. The one I'm looking for is not it. Therefore, this is Aristotelian logic. The only leftover possibility is that the cube of this guy must be generated at loop level. Because if it were at tree level, I get a contradiction. It doesn't happen. Okay? At 4, and I want to do this also at 4 because it uses this. Okay? At 4, there is one graph that can generate an object with 4 external lines. Okay, I'm going to erase this because I'm not going to use this. So for n equal to 3, that's the way it goes. For n equal to 4, the graph is this. Now, in between here by Lorentz invariance, it has to be a boson. So it has to be a scalar or a vector boson. Scalar or vector boson. This is a light guy, so I'm going to A, light guy, light guy, light guy. So this can be a heavy guy, and I'm going to exclude the case where this guy is a heavy one. So let me look at this possibility. Well, this possibility has an internal line, great things. This has a propagator that was like 1 over p squared plus minus a heavy mass, lambda squared. So when lambda is or momentum is small compared to lambda, I get my 1 over lambda squared. I'm getting encouraged. Okay, this is actually working out for me until you realize what this vertex here, where does this vertex come from? Again, it comes from this guy. It's a three-field vertex. It comes only from the Lagrangian. That's where the only origin. And what do I have? Well, this is my Lagrangian, and so it has to come from a product of a term like this with a term like this. That is the only vertex in the Lagrangian that has 3 gauge bosons, and therefore it is proportional to the structure constant involving 2 light fields and a heavy guy, which is 0. So the graph is 0 because of this. And you might object and say, wait a minute, but you told me you can generate it also with the scalar in between. That is true. That is true. I'll come back to that later. But this illustrates how at least this condition prevents the heavy gauge bosons from generating my friend here. I'm sorry, a section of this friend here, the one that has 4 gauge bosons in it. Other questions? The rest of the calculation or the rest of the argument is based again and again on properties of the group, properties of spontaneous symmetry breaking, things like that. So I'm going to mention them, but it will be exhausting for me and much more for you, for me to actually go through all the calculations in detail. And unfortunately, I can tell you things, but you have to think them through. So it's impossible for me to force you to think them through. So I'm just going to mention how things go and think them through. If you have questions, then I'm here until Friday, okay? And the reason I'm asking you to, or suggesting to you that this is a worthy exercise to go through this thinking process is precisely this argument here. You want, it's okay. The interpretation of the experimental results require us to understand the nature of the operators at hand. And this is the process of doing that. All right. Next up, fermions. So the fermions, the term in the Lagrangian that connects fermions and vectors are just the kinetic pieces. It involves the covariant derivative. And this is for the whole theory, the underlying theory, which I remind you, I've assumed is a generic gauge theory. In it, I have fermion fields that I call collectively chi. And there's little psi, which are light, and big psi, which are heavy. And again, I have my vectors v, and the vectors v also have light and heavy, A and X. Right? And then I have a property of group theory in spontaneously broken gauge theories. That is, the generators of the algebra of the group, the group generators are associated with either light guys or heavy guys, and the ones for the light guys I will call the unbroken generators, and these just do not mix representations with different mass, just don't. And therefore, there will be no vertex that has one light, one heavy, and one light guy. I must have a light vector boson because this is a property only of the generators associated with light gauge bosons. And then this type of object is excluded. You can still have operators with 2 lights and 2 heavies, and you can have a mixed guy with a heavy guy, but you cannot have light, heavy, light. If you remember, in the previous, we cannot have a light, heavy, light. We couldn't have 3 gauge bosons, 2 light, 1 heavy. Here, we cannot have three fermions, a triple vertex involving fermions, 2 light and 1 2 light and 1 heavy of this kind. Okay, but we can have this type, which is light, light, heavy. Okay, but just like that. So another way of saying it, so far, the A guys connect either to 2 heavy or to 2 light, but not to a heavy light. I encourage you to think this through. And a little bit more complicated, are the scalar part. The scalar guys, I denote by this by theta. The full gamut of scalars I call theta that are separated into little phi, which are light, and big phi are heavy. You see a pattern here. Capital Greek letters for me in this calculation are heavy. Small case Greek letters are light concerning the matter fields. For the gauge fields, it's A and X. Yes? You have a counterexample. Tell me later.
You have this heavy vehicle like Formal,
A heavy vector-like fermion.
let's say top partner,
Okay, all right. I need to write it down. I need to make time to try to think how to answer this.
what is wrong here?
Yes, well, okay. So you have a heavy
So let's say heavy vehicle like what? Capital Q.
vector-like quark. Is it a doublet?
That
No, you have to tell me. It's your model.
sorry? Okay.
It's a doublet?
If it's a singlet,
Okay, it's a singlet. And then it's a right-handed singlet? No, vector-like. Vector-like. Singlet. Singlet. And?
and it goes to it has a vertex, let's say, because I know the decay like it goes to light quark and there is standard model.
Okay, so what you want is this Q guy goes into a light quark
And the standard model,
and a standard model case.
or standard model gauge goes on, let's say Z.
Or a Z. Okay. How does this happen in your model?
Not my model, I'm just saying.
It's your model, you're telling me.
It's all these top partner charts, let's say, has this.
Okay, so let's see how it can possibly be. Let's see how it can possibly be. It's supposed to happen at tree level.
Yeah.
Tree level. Okay, tree level graph. And so you have one. We just argued that the tree level graph, a process with 3 external guys, looks like this. Q, Q, Z. How do you generate this?
You have to be doublet. Otherwise
No, so you
Oh, he told me it's a singlet.
let's say you have a standard model one doublet and a Higgs and a right-handed and this vector like quark.
Okay,
It's the same charge as the right-handed quark.
okay. So I have,
Let's say I can go and write down that. Standard model left-handed quark doublet
sun model, left-handed quark doublet
with the Higgs.
with the Higgs.
Okay. And so in the Ecoba introduction, what you write? You replace this with the right-handed quark, right?
Q,
So let's say this capital Q has the charge of a right-handed quark.
okay,
Then this is a perfectly allowed term.
okay.
And then you diagonalize.
And you have a term that goes like this. MQ Q bar Q.
Yeah.
And the hypercharges somehow arrange themselves. Okay. And this is the Lagrangian. Okay. And
And
what else?
when heats get the waves, it mixes these two things, the quarks.
Okay, but
You diagonalize it and you go to mass basis, but somehow this.
okay, the Z comes from where?
Sorry?
The Z.
Oh, there is a coupling of, let's say, if this Q can have E1y hypercharge, the small Q can have E1y hypercharge.
ID slash.
Yeah, and from there, when you diagonalize the mass basis, they have a coupling with the Z of diagonal coupling.
Okay. All right. And what you want is from here to get what?
You have also Q, small Q bar D slash small Q term. The usual kinetic term for standard model quark.
Okay. More. And you want this also? Yep.
No mass.
Right? Yukawa and so on. Okay.
It will be different. It will not be with the same Q. It will be left and right. Yeah.
What is left and right?
Yukawa will not be with the doublet. Both of them will not be with the head.
Come to right. You're right. So there's no mass. You're right. Sorry. Sorry. There's no mass? Okay. Q.
So you write down the mass matrix for these two quarks, right? What is 2 by 2 mass matrix, diagonalize it.
Yeah.
Generate this vertex, right? These
Or
are
to
all
go-
the standard searches are going on.
No, I understand what you're saying. So what Sanjay is saying is from here, one can get the mass matrix for this. When this gets a web, you have something like this. Mass matrix, QQ is M. Let me just call it big M, okay? So I have fewer labels. I have a
Yeah, so one of these off-diagonal
Vev.
one will be non-zero.
I have a bev, I have a 0 here.
No, I think that will be Yukawa. Another diagonal will be there.
So it's light. 0. Okay, well, okay, so it's a Yukawa.
And one of the off-diagonal will be 0, the other will be non-zero.
Not exact. Okay.
It will be a one of the
All right. I'll have to work through the model itself because this is not quite the end of the story, right? You have the right-handed guys and so on. But so this is for you a counterexample to this statement, right? To this guy. Because there's mixing.
Oh, no, there is a statement. So that's what the unbroken generator, TL them out. But this statement will be when the X vector.
I'm saying, I was going to say, I was about to say, you're relying,
On the
okay,
generator. Yeah.
so where he screwed up,
Fine, but I got the point.
where he screwed up, no, I'm sorry. No, what I meant, why are we arguing? Because the whole point is that the mixing that he's relying upon requires the Higgs to get the vacuum expectation value. When that happens, the light generators get broken. In the standard model, there's three broken generators. We get 3 heavy guys, 1 massless photon. I am looking at the theory when the spontaneous symmetry breaking, if any, occurs only at the high energy limit and not yet at the level of the light theory. So another way of saying it is if you allow for the breaking of the standard model, this is true up to small factors. In my world, small factor is 250 GeV. That's small. That's light. Okay, so that's small.
Is there any possibility for radiative correction?
For a
Is there any possible contribution of radiative correction with the tree level?
Oh yes, everything is at tree level. If you have radiative corrections, this happens. Radiative corrections generates this thing. generate this guy, will generate everything. But the point of this is that all radiative corrections come with this suppression factor. It's just a numerical factor that's useful phenomenologically, the 1 over 16 pi squared. Okay, that's the whole thing. But yes, you're absolutely right. The radiative corrections, they generate anything. In fact, they generate everything. And so, yeah, absolutely. Okay. So the low energy theory, yeah, but thank you. That illustrates something I should have super emphasized and I didn't, which is the low energy symmetry is not broken. Not broken. You can say how that can be is that in my world, I'm at a temperature of 257 degrees, 250 GeV, degrees Kelvin equivalent. And so the standard model is not broken. But the lambda is much larger than 256 GeV by assumption. And so even at my hot temperature of I don't know how many 10 to the x degrees Kelvin, the underlying symmetry, if broken, is still broken. I mean, it's not okay. All right. Thank you, Sanjay. That's very useful. Okay, then let me look at the scalar vector interactions. This comes from this guy, and I'm going back in time. Okay, so when and if a heavy guy gets a VEV, it generates terms that have two vector bosons and a scalar. Because, you know, this is the usual thing of spontaneously broken gauge theories. I want to examine this vertex. And so it looks like this. I've actually expanded it. This is the VEV. It comes from one of these guys. And here are two generators. This comes from the covariant derivative. And there's the vectors associated with it. And then I have another scalar field here. Now, as in the other case, the unbroken generators do not mix heavy and light. And because they are unbroken, they annihilate the vacuum expectation value of this guy, because they're unbroken. That's the definition of unbroken. And so, if this is a light guy, you will get 0, and the corresponding cubic vertex of it will vanish. Okay, so that's the type of argument. I'm not going to go through what it implies in all possible situations, but in this case, that's what it implies. Okay. Another observation. These are the broken generators, the heavy guys. This object here points along a Goldstone direction. And therefore, it is orthogonal to the physical directions, be it heavy or light. And finally, gauge transformations do not mix the physical guys with the Goldstone directions. And all that says this. That if you have a heavy generator and any other generator acting on a light guy and a heavy VEV on the left, you get 0. This shows up here. So I use those two things, this and this, to again exclude a bunch of vertices. In fact, 11 out of 31. These are the ones that are allowed. For the scalar and vectors, these are for the fermions and vectors, and these are the forbidden ones. This vertex of 3 light guys is forbidden because the standard model, the phi is a doublet, so you cannot make a singlet out of 3 doublets. The other ones involve some of the heavy fields, and so they do require the arguments I have been using. So these two conditions, that this is true, and this is true here at the bottom, and this is true here at the bottom, imply that a light, heavy, light, heavy, heavy, and so on vertices are 0. This vertex doesn't occur because I have not broken the standard model symmetry. That is another. When you break the standard model symmetry, you will generate a Higgs ZZ vertex, right? But since I have not broken it, this just doesn't show up. And the quartic vertices forbidden are these guys for those involving bosons only. So what do I do with this? I found the vertices that are allowed and the vertices that are not allowed. And with it, I can construct painstakingly all possible graphs that have propagators that are heavy, here denoted by a heavy line, and they may be either bosonic, indicated by a dotted line, and that implies also gauge bosons, not only scalars, or fermionic, indicated by a continuous line with an arrow here. All the external guys are light. The heavy dots denote super-renormalizable vertices of coefficients of order lambda, which I told you already they are problematic, very problematic, but I'm listing them anyway to be as complete as possible. These are all the possible graphs and kind of thing. If you don't put in coefficients of order lambda here and here, this graph is not of order 1 over lambda squared, but in fact is of order 1 over lambda to the 4th. It's easy to check. And so that's why it necessitates this thing. Any graph that you might cook up that is not in this list because it involves one of these vertices in one way or another. So this is, this project, when I went through it, had 3 painful stages. And painful stage number 1 was doing this. Painful stage number 2 was doing this, finding which graphs are allowed. And the last painful stage was to look at these graphs that I generate, that embody, by the way, all possible terms, all possible graphs at tree level that can generate, that have a coefficient of 1 over lambda squared. Okay, so these are the graphs that correspond to my dimension 6 operators. And the last painful stage was to match these graphs to the list of operators that I showed you a few lectures ago for the standard model. Some of the operators will correspond to nothing here. So for example, you see no graph that has 3 dotted external lines. These are the ones that I've excluded earlier today. Those are the ones that are forbidden at tree level. There are graphs, the operators, that certainly show up with this guy. Paramount among these is a 4 Fermi interaction. 4 Fermi interaction. It has 4 fermions outside and a boson in the middle. And the thing that can be generated at tree level by some boson in the middle. Okay? In contrast, operators with 3 bosons outside cannot be generated by anything. In a tree level. There's nothing you can do. You might say, what happens if my theory doesn't have that boson? Well, in that case, this operator that could be generated at tree level, in your theory, isn't. It's generated, if at all, by some other means using gradative corrections, because you don't have the right intermediary to do this. Okay, so that's why I call them potentially tree-level generators. If you have the right type of heavy physics, you generate them. If you don't, well, you may still generate them, but not at tree level. On the other hand, the loop-generated guys are always generated loop, no matter what kind of new physics you choose. All right, so here's the list, half of the list of operators that I showed you earlier, and I've highlighted those that are potentially tree-generated. All the other guys that you see here, triple vector bosons, 2 vector bosons, 2 scalars, this that look like, these have 2 fermions and a W and a scalar and have like a magnetic coupling. All these guys have very cool experimental signatures and would be observable if the coefficient weren't suppressed by this 1/16 pi squared. But reality being what it is, the 1/16 pi squared is there, and though the effects look cool, they're tiny, too small to be seen. So let me describe briefly what these guys are. Yeah, these represent changes in the self-interaction of the Higgs. This guy is interesting. It is the oblique t parameter. The coefficient of this guy represents deviations from the standard model of the oblique t parameter. This guy are Yukawa-like. This part is precisely the standard model Yukawa. It's multiplied by 2 scalar fields. This guy, as I mentioned briefly some time ago, generate in corrections to the interaction between the gauge bosons and the fermions, like the Z and the W. In fact, all these are the corrections to the Z coupling to the fermions, leptons, left-handed leptons, right-handed leptons, and quarks. And this one at the bottom that's covered by this thing, I apologize, is a correction to the coupling of the W to the up and down quark. There is no correction to the W coupling to the electron and the neutrino. There's no counterpart of this guy. It's forbidden by gauge invariance. And then all the 4 Fermi interactions, all of them can be generated at tree level. Now, you may say, well, how do you know? And the answer is, I can't know a priori. I can know a priori that all these guys have small effects. Whether these guys have small effects or not, small, I mean suppressed by this loop factor, depends on the underlying new physics. For some kinds of new physics, this happens no problem at tree level. Other kinds of new physics, it happens only in loops. In fact, let me point out something. Yeah, how can you ensure? How could I ensure? Let me illustrate this. These are what I'm telling you is that these are all the possible graphs that give you terms of 1 over lambda squared when you integrate out the heavy guys. These are all the, and they have one thing in common. All the graphs have at least one vertex that involves 2 light particles and 1 heavy guy. 2 light particles, 1 heavy guy. 2 light particles, 1 heavy guy. 2 light, 1 heavy, and so on. All of them are. Okay? So imagine a type of new physics where that has a discrete symmetry. All the light guys, the standard model, is even under that symmetry. All the heavy guys are odd under that symmetry. Okay? And assume that that symmetry is not broken. That means that terms that have 2 lights and 1 heavy are forbidden. All these vertices that I mentioned are forbidden. All these graphs are forbidden. And therefore, none of the operators can be generated at tree level by this type of new physics. And you know or have heard of an example of this. Supersymmetry. The parity thing is R parity. R parity. R parity forbids then the heavy guys in this version of supersymmetry are all the super partners to the fermions and the gauge boson. All the super partners, in fact, and all the super partners. And so those are odd under R parity, all the normal guys are even on their arc parity. And therefore, if you imagine that all the superpartners are heavy, then their effects at low energy are always suppressed by 1/16 pi squared. That is a very good reason why supersymmetry has been so successfully surviving over all these years, because the corrections it produces are small. Many of the corrections that you look at supersymmetry is because the theory requires two scalar doublets. And so there's a lot of an almost infinite number of papers that talk about the two Higgs doublet model. And it's partly motivated by supersymmetry. But I'm not talking about a case where the two Higgs doublet models are the heavy physics. I'm talking a case where all the supersymmetric particles are the heavy guys. The low energy theory, in this case, has an extra doublet. Fine. You know, that's the way it goes. But the heavy particles, the one that guarantee you have supersymmetry, all their effects are suppressed by 1/16 pi squared. Not only by their mass, by their heavy mass, but by this loop factor. And therefore, they are very well hidden. There are other examples of this thing, but I will not go into them. I think it's a good thing to keep in mind that one can find easily, by this simple argument of a parity symmetry, models of new physics that generate all operators, all these operators at loop level. So, purple, potential tree level generated, not purple, loop generated. So which one of these? Again, let me reemphasize, you have self-Higgs interactions, you have the T parameter, you have your Kawa-like couplings, you have the WZ couplings, and you have 4 fermion interactions. Those are your windows into new physics. In most cases. I will come, when I go at the applications, one case that I know of, very clear, where loop-generated operators actually are of interest, and we can probe them. But that's a very specific case. Okay. Any questions? Okay, let me finish by doing just a few observations. I've constructed for you almost to the end that the number of PTG operators is 1 in dimension 5. I constructed it. It was this Weinberg operator, and you probably know it. If not, I really encourage you to go and check it out. That the operator can be generated at tree level by precisely 3 types of new physics. It's a very elegant and interesting fact. In dimension 6, I did not count them for you, but the purple guys here are 39 of them for 1 generation. In dimension 7, there's 20 of them. I'm not listing them at the moment. And again, let me re-emphasize that presumably the largest NP effects that we can observe come from the PTG operators. Okay. There are, and again, this last statement, there are 1 loop process in the standard model that are very interesting and are readily measured, and such as the decay of the Higgs into 2 gluons. That's how the Higgs is produced at the LHC. Since we measure the Higgs, we measure this. Okay? And for these rather rare type of processes, the loop generated operators will also be important. But this is a rare instance. And with that, let me stop. Any questions? Okay, so the takeaways from today. It's a long formal set of calculations. First, the hierarchy defined by the effective theory is consistent with renormalization. Whether you want to do renormalization or not, which I recommend you do not, but it's a free country, it's different. you can be reassured that the model, the theory is internally consistent in that sense. Second thing, one can segregate operators into those that are generated at tree level and at loop level. The ones that are generated at loop level have that property always. The ones that I identified as potentially tree generated may or may not have that property. And I've argued for the phenomenological benefit of doing that classification and obtaining it. This is actually useful in that respect. You can do this not only for dimension 6. It's more painful to do it for dimension 8 and dimension 9 and so on. Shubha and I did it for dimension 7, and that was not fun. So I don't recommend dimension 8, but again, it's a free country to do it. Just keep in mind that there are very, very few processes that are sensitive to dimension 8 and 9 operators. And so, again, whether there's payoff at the end of such a big effort. Okay. What I'll cover tomorrow is applications. I will cover applications such as neutrinoless double beta decay. Well, there's no secret. I will talk about Higgs physics, simplified. I'll talk about neutrino physics a little bit, and talk about lepton number violation in the guise of the neutrinoless double beta decay. But that is tomorrow. That is tomorrow. Today, I'm done. I'm sorry, I'm done with this. But any questions? I'm babbling on in the hope that some of you will be brave enough to ask a question that might be nagging you. And okay, all right, thank you.